Hey guys, today just want to talk about that the 2.4, the piece Y, no, the precise definition of a limit, excuse me. So the precise definition of limit regarding delta and epsilon. So according to the definition, we do have limit of f of x, x approaches a equals L. And if for every number epsilon, it's greater than 0, there's a number delta, it's greater than such that if 0 is less than absolute value of x minus a, it's less than delta. Then absolute value of f of x minus L, it's less than epsilon. And according to the definition, so epsilon and delta, so we do know that those are the arbitrary, very small decimals. So it's almost getting close to 0. Okay? The reason why we're doing this, because we want to find out, the close possibility of the value of x and a, and also the limit, and also f of x, or actually f of a. So now we'll see that one of the example in a minute. So for the first one is using the given graph of f to find a number delta such that if 0 is less than absolute value of x minus 5 is less than delta, and then absolute value of f of x minus 3 is less than 0.6. So anytime that you started with a conditional statement, and a lot of people thought that we need to start it with the hypothesis first. But for the precise definition of limit, so the way that you need to start it with, it's always the conclusion. Once we started off with the conclusion, we can find out the value of f of x, or the value of x. So now let's start it off with this one here. So f of x minus 3, it's less than 0.6. So back to algebra 1 or algebra 2. The way to solve for the absolute value inequality, it's always by undoing the absolute value. So we want to make it as positive and negative. So for the positive, we just want to end up with f of x minus 3. It's less than 0.6. And then for the negative, so we want to convert that to its opposite. So it's greater than negative 0.6. So for the positive, we solve for f of x. So 0.6 plus 3, which is what? 3.6. And f of x is greater than negative 0.6 plus 3, which is 2.4. Again, less than, greater than, that means it's about. Okay, so it's getting very close to 3.6, and this one is getting very close to 2.4. Now the thing is that we don't know what f of x is, but the graph is given already. So back to the graph right here. So for the value of 3.6, so the corresponding value, which is 5.7. Okay, so this one, just refer back to the graph. So it's 5.7. And for those students might be wondering what happens if f of x is given, so you can solve for x from here. But now, in the other one, 2.4, so 2.4, just refer back to the graph. So we do have 4. So x is about 4 right here. Again, it's about, well, it's not exactly, it's very close. And then, once we find out the x value, we just want to refer back to the hypothesis. So for the hypothesis, we do know that 0, it's less than absolute value of x minus 5, it's less than delta. So let's just plug in those two x value, okay, one x value at a time. So we got 5.7 minus 5. Okay, so which is 0.7, absolute value of 0.7, it's 0.7. So delta, it's about 0.7. Again, less than, greater than, it doesn't really matter, it's about, okay? And then for x equals 4, so we do have 4 minus 5, it's less than delta, which means it's absolute value of negative 1, which is 1. It's about, well, that's the value of delta. So now, you want to compare those two deltas values, so which one do you want to choose? Again, by definition, delta is a very small decimal, so we want to choose that 0.7. So that's the answer for delta. So now, regarding the proof. So for those you might be wondering, do the proof. Okay, so let's do one like this. So this one proved the following statement using that epsilon delta definition of limit. So let's do A. So this one is showing that limit of x over 4 plus 3, it's linear functions. as x approaches 6. So the limit, it's 9 over 2, which is 4.5. So once again, we're going to use the definition of limit, the precise definition of limit. So this one, so you want to identify the value of a. So a, which is what, 6. Because that x is approaching 6 right here. And then the given functions, which is considered f of x. So it's x over 4 plus 3. And then L, which is the limit, the exact value of the limit, 9 over 2. So now, according to the definition, if 0 is less than absolute value of x minus 6, it's less than delta, then absolute value of f of x minus 9 over 2, it's less than epsilon. Again, f of x, that's given already, which is considered x over 4 plus 3. So once again, first thing that you want to do, you want to start it off with the conclusion. So combine the like terms. So we have x over 4 plus 3 minus 9 half. So 3 is considered 6 over 2. So we do end up with negative 3 half. It's less than epsilon. And now from here, we want to take out the greatest common factor. So the greatest common factor here, which is considered 1 over 4. Absolute value of 1 over 4 is 1 over 4 again. So we do have x minus 6. It's less than epsilon, because 6 times 1, 4, which is what? 3 half. And now from here, we want to solve for absolute value of x minus 6. So multiply everything by 4. So we do have absolute value of x minus 6 is less than 4 times epsilon. And now back to the hypothesis. So just compare and contrast. One thing that you realize that x minus 6, absolute value of the whole quantity, x minus 6. And that's almost the same as 4 times epsilon. So this one, basically, we can just replace that by 4 times epsilon, because that they're almost exactly the same. Again, less than, greater than, that means about. And then we want to put it in for that absolute value of x minus 6. So simply just replace it. And this one is almost getting close to delta. And then the last thing that you want to do, you want to solve for epsilon. So epsilon, it's about delta over 4. So again, the final proof is that you want to show the relationship of epsilon and delta and see which one is smaller. Okay, it's always the connection between epsilon and delta. So therefore, so that'll be the proof. Okay, so now let's try another problem with another proof. So another one is limit for the quadratic function. It's a quadratic trinomial. X squared minus 4x plus 5 as x approaches 2, so that equals 1. So let's find out the proof for this. Again, it's a quite similar structure. The only thing that we change is just the x value, the value of a, the functions, and the limit. So this one, given that limit, x approaches 2, x squared minus 4x plus 5 equals 1. So obviously a is 2, f of x. It's x squared minus 4x plus 5. And then L, which is 1. Again, just rewrite it with the conditional statement. So if 0 is less than absolute value of x minus 2, so basically just reset the conditional statement. It's less than delta, then absolute value of f of x, which is x squared minus 4x plus 5, minus L minus 1. Okay, L, which is what, the limit, so that's 1. So that's less than epsilon. Again, let's start it off with the conclusion. So the conclusion that we have, so this one would be considered x squared minus 4x plus 4. It's less than epsilon. So what I did here is just combine the like term. And then the trinomial, so basically we can factor it, so it's x minus 2 quantity squared. Again, it's a perfect square trinomial, so that's why it's considered x minus 2 quantity squared. And then exponent, so you want to find out the way to simplify that exponent, so take the square root both sides. So we do have absolute value of x minus 2, it's less than square root of epsilon. Again, epsilon, it's a very small decimal. It's almost getting close to 0. And now, back to the hypothesis, compare and contrast. So one thing that we notice, absolute value of x minus 2 is about square root of epsilon. So simply replace this, square root of epsilon, it's less than delta. And now the last thing that you want to do, you want to solve for epsilon in terms of delta. So that means epsilon, well, you can square both sides. Square both sides. So we do have epsilon, it's about delta squared. Again, great. So anytime they want to do the precise limit definitions for the epsilon delta, it's all about using the connections, the hypothesis, and the conclusion. Again, it doesn't matter whether that you're solving it, finding the value of delta, or proving it, always start with the conclusion. Okay? And thank you for watching the video today.